In the last session, and in session 3.1, we have learned about joint orientation, on how to measure them and how to express them in terms of dip direction and dip angle. In this session, session 5.7, I want to show you how we can use the hemispherical projection technique to analyze the orientation data. Imagine if you wanted to present a plane on a piece of paper. You can draw the plane in the 3D perspective drawing. If you ask to draw another plane on the same paper, it is getting a bit messy and mixed between the two planes. Color may help to differentiate. But imagine you have to draw 3, 4, or 10, or even 100 planes. I don't think you can possibly do that. Conclusion: presenting several planes together on plan is very difficult, if not impossible, by normal means. Geographical projection is pretty common to have an image of a three-dimensional object projected onto a plane, for example, on a piece of paper. It is a graphical method, not mathematically to calculate and plot. The word map we see on plan are typically the projection of the spherical Earth. There are several methods of projections. You can easily find the explanations from the books and the internet. The one we use in rock mechanics and in geology is the lower hemispherical projection. It allows us to transform planes and the lines in 3D space onto a 2D plane. In lower hemispherical projection, we use the lower half of the sphere. A projection plane is the plane on which the projection will be made. In our lower hemispherical projection, the projection plane is the equatorial plane. It is the horizontal plane through the center. The zenith point is the center of the projection. That is, all the projection will converge to the zenith point. The zenith point in our lower hemispherical projection is the top of the sphere. Now, let us look at planes intersect with the lower hemisphere and how they look like when projected. Start from the left. Projections of vertical plane. If the vertical plane is cut through the hemispherical through the center, we will see from the diagram in the middle that the vertical plane will have a trace line on the hemisphere. The trace line is in fact a semicircle laying vertically right at the bottom of the sphere. If you project this vertical semicircle to the horizontal plane, what will you get? You'll get a straight diametrical line as shown by the dotted line in the middle figure below. You see that a vertical plane in space by hemispherical projection, it is now presented by a diametrical straight line on the plane. Similarly, if you put a horizontal plane through the hemisphere and through the center, it cuts exactly the circumference of the hemisphere. The trace line is a full circle, laying horizontally. So the projection on the horizontal plane is the full circle. It shows that a horizontal plane by hemispherical projection is represented by the circumference of the circle on the plane. Let us continue with more examples on inclined planes. When an inclined plane cuts through the hemisphere, it again leaves a semicircular trace line on the side of the hemisphere, on the side of the plane dipping towards 2. If you project this semicircle to the horizontal plane, you expect an arc shown by the dotted arc curve here. When a plane has a steep dip angle, the projection is an arc closer to the diametrical line. For a plane of gentle dip angle, the projection is an arc closer to the circumference. This is shown by the left and the middle projection diagram. The diagram on the right is a projection of an inclined plane dipping towards another direction. Compare one on the left. If you compare with the diagram on the left, you can see the difference of the projections of 2 planes of different dip directions. The 2 arcs representing the 2 planes bending towards different directions. To summarize the method of projection of a plane, first, let the inclined plane cut the reference hemisphere through the center. Second, the trace of the plane on the hemisphere is a semicircle. A horizontal plane leaves a horizontal circle. A vertical plane leaves a vertical semicircle. And an inclined plane leaves an inclined semicircle. And third, the semicircle is projected to the horizontal plane by condensing the images to the zenith of the sphere. The projection of a semicircle on the horizontal plane is typically an arc. A vertical line becomes a straight arc, which is straight line. A horizontal plane becomes a full circular arc, which becomes a full circle, as we've seen in the last 2 slides. Now let us take a look at the projection of a line, vertical, horizontal, or inclined line. As shown on the left diagram, the mark left by a vertical line on the hemisphere is on the bottom of the sphere. By projection, the mark on the bottom of the hemisphere onto the horizontal plane, it is the point right on the center. The horizontal line will cut the sphere with two marks on the horizontal circumference. So on plane, you will have 2 points as shown in the middle diagram. The inclined line will make a mark on the hemisphere. The location of the mark is governed by the trend and the plunge of the line. By projection, the mark becomes a point on the plane. A steep line will be represented by a point closer to the center. The trend controls the location of the point. In the right diagram, the line plunges towards southwest. So the point is in the southwest zone of the projected plane. To summarize the projection of a line using the hemispherical projection method, the same principle is also applied. You need to remember that a line leaves a point mark on the hemisphere. With projection, it will be a point on the horizontal plane. The position of the point on plane is related to the orientation of the line. With projection, a vertical line is represented by a point at the center. A horizontal line becomes 2 points on the circumference. An inclined line becomes a point in the zone of its trend direction. We know that a plane has a normal. Sometimes it is called a pole. The pole is perpendicular to the plane. It plunges to the opposite direction to the plane, and it makes 90-degree angle with the plane. On projection, we'll have the plane represented in green. The pole is a line, so it will be showing on the projection as a point. Since the pole's trend is opposite to the plane's direction, the point representing the pole is on the other side of the plane to the arc that representing the plane. As shown in the diagrams on the right, the plane is dipping towards southwest, so the pole must plunge towards northeast. That is, the point is in the northeast quarter of the circle. Since the pole makes 90-degree angle with the plane, the angle between the plane, which is the arc, and the point, which is the pole, is 90 degrees. Therefore, the point must be 90 degrees away from the arc measured along on the projection plane. We have already seen from the previous examples, when the plane dips towards southwest, the arc representing the plane on the projection bend towards southwest. Through the lower hemispherical projection, the arc's bending direction representing the plane's dip direction. Therefore, changing the dip direction of a plane through projection is shown by the changing of bending direction of the arc. The arc itself will not changing the shape. In other words, when you turn the plane around horizontally, you turn the arc around the center on the projected plane. What happens to the projection if you turn the plane vertically? That is, changing the dip angle. Well, we can work it out quickly. Remember, a vertical plane by projection is a diametrical line, and a horizontal plane by projection is a circle. So a plane closer to the vertical will give you an arc closer to the diametrical line and also more straight or less curved. On the other hand, if the plane is subhorizontal, then you will have a projected arc further away from the diametrical line and bend to closer to the circumference, which representing a horizontal plane. So, as we showing on this slide, change of dip angle results in the change of curvature of the arc. Increasing dip angle of the plane from 0, that is horizontal, to 90, that is vertical, will lead to the decrease of arc curvature from a circular to a straight line. Again, remember, when dip is 0, arc becomes a circle, and then when dip is 90, arc becomes a straight line. The projected dip angle is coming from the circumference towards the center. We have covered the principle of lower hemispherical projection method. I want to continue to show how we actually do the projection. Of course, you will find all those projections now can be done by computer. You key in the orientation of the joint planes, and the computer will give you the arcs or the points. But I'm sure you do not want to be blindfolded in a year and make decisions with a black box. Once you learn how to do the projection, it is rather simple and indeed fun to use it. The projection done manually is in fact done by drawing the projected arc or point on a tracing paper over a printed stereographic net. The tracing paper is pinned to the center of the stereographic base net so that the tracing paper can rotate around the center. The projection is drawn on a tracing paper using the stereographic net below. You can read more about the stereographic net from the books and the internet. The stereographic net normally uses in rocket mechanics and also used in this session is the equal area net, shown by the big net on the right. Let us learn the projection method and techniques through practice. We will first do the projection of a line with a trend of 170 and a plunge of 35. We always start by placing a tracing paper over the stereographic net and use a thumbtack pin from the back of the base net through the center of the net and then the tracing paper. So when you put the pin, the net and tracing paper on the table, the tracing paper can rotate freely. I normally will draw the big full circle around the circumference first. Now we are ready to draw the projection. The steps are highlighted on the left in words and illustrated on the right drawing. We'll follow step by step. Step 1, we draw and then mark the top 0 degree as north. This is usually called home position. It is not only for noting the north, but also give us the reference point for the tracing paper to return to its starting point, the home position. Step 2, the trend of the line is 170. It is almost to the south. This is the direction measured from the north clockwise. Therefore, on the projection, we count 170 degrees clockwise from the north and mark a clear mark on the tracing paper on the circumference. This is the direction of the line pointing to 170 degrees. Now we have got the trend located. Step 3. Next is to mark the plunge angle. It is 35 degrees measured from horizontal. So we needed to measure 35 from the circumference, which is horizontal. The position we measure vertical angle is along the 90 to 70 line on the net. Simply because you can read the measurement along this line. So we turn the marked point of 170 to coincide the horizontal diameter, either 90 or 270 on the net, whichever is convenient. So you can turn clockwise or anti-clockwise to make sure the 170 mark is lying horizontally on 90 or 270. Then you count 35 from the circumference along this horizontal line. From circumference towards the center for 35 degrees and mark that particular point with 35-degree counts. Step 4. At the moment, the tracing paper is not at the starting position, as it has been turned in step 3. So we need to return to the home position by turning the tracing paper so the north point is indeed on the north of the net. The point you have marked in step 3 is the projection of line 170, 35. So you can put a note of 170 slash 35 next to the point as the final step to indicate the point is the projection of the line with trend of 170 and the plunge of 35. If we remove the tracing paper from the base stereographic net, we will have the drawing on the tracing paper looks exactly like the one shown here. The point representing the line 170, 35 is below the center. Taking the center as a reference, the marked point is towards 170, almost south, and is 35 degrees from the circumference towards the center, or 55 degrees away from the center. Usually, you should try to visualize the projection before you actually start doing it on paper. Seeing that a line is plunging towards 170, nearly south, when it intersects the lower hemisphere, where do you think it will leave the mark on the hemisphere? It will leave the mark on the southern side of the hemisphere, almost directly to the south. The 35-degree plunge angle will suggest the mark is closer to the circumference instead of the center. By doing that, you should have already imagined that the projection of the line in your mind, and you should always compare your imagined projection in your mind to the drawing that you get from the paper. They should match. If not, you may have to think again or look at the drawing again. Let us move on to do the projection of a plane 170 and 35. Again, tracing paper above the stereographic net, thumbtack pin at the center, drawing the full circle on the tracing paper. Then we take step 1, mark the home position on the north. Step 2, count 170 degrees clockwise from the north and make a mark. Step 3, turn the 170 mark to coincide the horizontal diameter of the net, either at 90 or 270. Count 35 from the circumference along the horizontal line and lightly mark the point. The point marked is in fact the line of 170, 35 as we just did. in the last exercise. This is the line of maximum dip on the inclined plane. It has the same orientation as the plane. We then follow the arc curve on the base net and draw the arc through 170 35 point. The arc curve is the plane with orientation 170 and 35. Step 4, again, we need to return the tracing paper to the home position to finish up the projection exercise. Write down a note of 170/35 beside the arc, and we have done the projection of plane 170 and 35. Again, remove the tracing paper from the base net. You will have the drawing on the tracing paper look exactly like the one here. It is an arc bending nearly right down towards the south. This is a projection of the plane with orientation 170 and 35. You can also do the mind projection as we mentioned in the last projection line. Again, visualizing in your mind will help you to check whether your drawing is right. I mentioned that the point marked with 170 and 35 is the line has the same orientation as the plane. This is a line of maximum dip on the inclined plane. You can draw many lines on a plane. In other words, a plane contains many lines. However, there is only one line have the maximum dip angle. The other lines will have smaller dip angle. If I put a small ball rolling down the plane, the path of that ball rolling down on the plane is the line of maximum dip with the maximum inclination angle on the plane. So this is the line of the steepest angle on the plane. The orientation of the plane has the same direction and the angle as the line of maximum dip on that particular plane. You have also experienced through your projection. Sometimes you need to determine the orientation of the projected planes and the lines. Well, you just need to reverse the projection processes we just done for the planes and the lines to find the direction and inclination of the line or the plane. I will not specifically show you here, but we will encounter this in the examples later, and you will be seeing how the orientations of the plane and the lines are determined through projection. The next example is to find the line of intersection of two planes. When two lines intersect, we'll have the intersection point. Similarly, When two planes intersect, the intersection is a line, usually called the line of intersection of two planes. In this example, we want to determine the orientation of the line of intersection through projection. The two planes have the orientation of 11050 and 19065. Since we are already familiar with the projection of the planes and the lines, you can easily do the step 1. Join the projections of plane of 1110 over 50 and the plane 190 over 65. They are the two arcs showing on the drawing on the right. The two arcs intersect. Then, as step 2, we mark the intersecting point of the two arcs. This intersection point represents the line of intersection of the two planes. So with those simple steps, we actually have found the line of intersection. By looking at the location of intersecting point on the drawing, we can visualize in our mind that the line is plunging to southeast around 140 with a rather steep angle since it is closer to the center. The next step is to determine the exact orientation of this particular line. This is done as a step 3. We draw a straight line from the center through the intersection point to the circumference. The line cuts the circumference at 135. That means the trend of the line is 135 degrees. The next step, step 4, is to find the plunge angle of the line. Since we can only measure the inclination from the 90 to 70 line on the net, we turned tracing paper so that the point of intersection is on the horizontal line of 90 to 170 line. Now we can read out the angle. Remember, 0 is at the circumference and the 90 is at the center. So we count the angle from outside, from circumference towards the center. It gives 54. That is the plunge of the line of intersection. From steps 3 and 4, we have determined the orientation of the line of intersection of the two planes. It is 135 and 54. You can write down the orientation beside the intersecting point on the drawing. For some of you who have good geometry, perhaps you can try to calculate the orientation of the line of intersection. I'm sure you will get the same answer, but it will take you quite a bit calculation, perhaps a page or 2. Start having fun with the projection. Let's do a couple more examples. This time, find the angle between two lines. When two non-parallel lines intersect, and they usually have an acute angle and a obtuse angle, unless they are perpendicular to each other. Now try to think, how do we physically measure the angle between the two lines? We have to have the two lines on the same plane and then measure. Effectively, we are measuring the angle between the two lines on the plane containing the two lines. Okay, we are going to do the same, but using the projection net. The two lines here have the orientation of 140 over 40 and 40 over 30. Step 1 is to plot the projections of the two lines. 140, 40, and the other line 40, 30. You have already learned to do that, and should be done it rather easily. There are 2 points as shown on the drawing here. Step 2 is to turn the tracing paper around until we can put the 2 points on the same arc on the base net. You can draw the arc that linking the 2 points. This arc is in fact representing the plane formed by the two lines, or the plane containing the two lines. Step 3 is to count the angle between the 2 points along the arc. You will get 78 degrees. This is the angle between the two lines. As we just stated, the physical measurements of the angle is done on the plane. Therefore, on projection, we must measure the angle on the arc that representing the plane. Again, geometrically, we can compute the angle. Most of you will find it is easier and perhaps more fun to using the projection method. It also gives you perhaps the physical sense of doing the measurements by projection. Now we will try something more practical and relevant to underground rock engineering related to mining or tunneling. In underground tunnels and mines, you can observe the trace lines of joints on the sidewalls, pillars, roofs, and bases. From those tracing lines, we can estimate the orientation of those joints. In this example, we are going to find the orientation of a joint plane which leaves trace lines on the 2 vertical walls. We have the trace lines plunging 20 degrees to the west on the south-facing wall, and another plunging 60 degrees to the north on the east-facing wall, as shown in the diagram below. We start by drawing the 2 vertical walls. The south facing vertical wall is the horizontal diametrical yellow line running east-west. The east-facing vertical wall is the vertical diametrical yellow line running northeast. Then we can plot the two trace lines on the walls. On the south-facing wall, which is a horizontal diametric line, we count 20 from the west, as it has plunged to the west. And this point representing the tracing line plunging 20 degrees to the west on the south-facing wall. Similarly, we count 60 degrees from the north on the vertical diametrical line and mark it as the trace line plunging 60 to the north on the east-facing wall. Those two trace lines are shown as two black dots here. The plane we're looking for is formed by the two trace lines, or by a different expression. The two trace lines are on the same plane. Step 2 is to turn around the tracing paper to make it that the 2 points is on the same arc on the base net. Draw the arc, follow the base net. The arc is in red arc, showing on the right diagram. And this is the plane formed by two trace lines on the two walls. At the same time, you can determine the dip angle from the circumference. It gives us approximately 60 degrees. The last step, step 3, is to return the tracing paper to home position and then to find the dip direction. We can see that the dip direction is 350 degrees. Now we have completed the task. Found the orientation of the plane that has trace lines on the walls. The plane has orientation of 350 and 60. You may want to try to reverse the exercise. Knowing the joint plane orientation is 350 and 60, having fun to work out that what will be the trace line plunge angles on the southeast facing wall and the northeast facing wall. I hope you had fun learning and using the hemispherical projection. This is a very useful tool in rock engineering, particularly in slope stability analysis, involves block sliding. This is the end of part 5, rock mechanics testing and analysis of the course on rock mechanics principles. Thank you for staying with us on learning rock mechanics, and I wish you all the best. Goodbye, 再见, au revoir, auf Wiedersehen.